Good. Okay, chemistry time. Mitchell, I'm surprised by you. Chemistry time.
Chemistry time.
Thank you, Kyla. We're talking about, let's name it, your book calls it light and quantized energy. Let's name it light. I want to be more specific than that. So light and the quantum mechanical model. Why might I have chosen to name it this instead of quantized energy? Obviously they're related. The book calls it quantized energy. I've called it the quantum mechanical model. Why might I want to use this instead?
You guys are going to talk about, well, it looks like.
Yeah, you cut Pagan off. She was going to tell us what we were going to talk about, which would have been nice for me. But yeah, you're right. We already know what the quantum mechanical model is because we did in the last chapter, and it was also your belt work, hence the review. So what we're going to do now is relate the quantum mechanical model of the atom, which we know a little bit about. We know its structure. We're going to relate that to quantized energy, which is why it's named that and what your book talks about, and we're going to relate it to light. Okay? So the first thing, thanks Mitch. So the first thing that we need to talk about, and this should be absolutely be a review because we've done this, well, at least all of us, I know everyone in here except for Peyton has done this at least twice. I assume Peyton has done it to state standard. So what up with this?
It's a wave.
It's a wave. And what's this thing?
Wait.
Oh.
No.
Oh, it's okay. What is this thing? I drew this thing in the middle. It's not actually part of the wave. I think that's why I threw you off, Kyla. Yeah, we can call it the origin. There's a lot of names for it. It kind of depends on what kind of wave we're talking about. Origin, baseline. Sometimes we see it called, what was that? What did you say?
Wave time is what I said.
I don't think that, you're talking about how it's wave time in chemistry time now. Yeah. Origin, baseline, there's another one, but I forget. It doesn't really matter. Your book calls it origin, so that's fine. I think the physical science book calls it baseline. Either is fine. Let's label the rest of the parts. I'm going to just put little dots on them. You tell me what they mean.
Crest.
Have you seen this before, Payne?
Mr. Kine, you helped me with my math homework. That was
Yeah, with the sine wave, but I didn't know if you've ever actually seen the diagram of
Oh,
it.
yeah.
But you have seen
Yeah.
it. Yes. Yeah. Crest, what's this one?
Trough.
What's this bit where we measure from crest to crest? Or
Wavelength.
that's the wavelength. And we did talk about this in physical science, but I want to make it clear to you that we use this abbreviation for wavelength. A lot of times,
Which is the Greek letter.
the Greek letter lambda. Lambda. Why do you think we use that for wavelength?
I spelled that so wrong.
You could guess with me. I think probably because we're talking about a length. So we would use L. That would be the geometric variable for length. But since that's already taken by geometric linear measurement, we would use the Greek letter. That's a lot of times how it goes. In science, we just use Greek letters because the Latin ones are already taken. What would I label? I'm going to do it over here because I don't want to intersect my other lines. Good. Everyone remembers these. It's just Mitch, because he's inquisible, is the one who keeps saying them right on the buzzer, like inquisible Mitch, right?
Yes.
But does anyone need more review than what you're getting? You remember these, Kyla? Peyton?
Yeah,
Alexis? Okay. Awesome. Let me make sure I got all of them here. Yep, that's all those are the most important ones. And then what this all leads to, this is review, as I said. What kind of things does this apply to?
Anything with a wave?
Anything with a wave, yeah. Too vague. What kind of specific things does this apply to? Light.
The
Sound.
ocean.
Light. Sound. The ocean. You're not wrong, Mitch. Hair. I mean, really, who here's got curly hair? I kind of do if it gets long enough. But we can measure the crest and trough of a wave of Peyton's hair. It'd be weird if we did that, but we could do it. It looks kind of like this. So if we just make it this, there we go. Now we've got Peyton's hair. But no, it's not wrong to do it that way. It's just that these two are obviously more scientifically valuable. Sorry, Peyton.
It's okay.
Thanks. But the one obviously that I keep using the word obviously, and it's probably hurting your feelings. But the one we're most worried about because it's the title of the chapter or the lesson is light. And so to that end, we need to memorize this equation. C equals lambda nu. Let's write that down. What are we going to do with this equation, do you reckon?
use it.
find the,
We don't use it.
We don't use it.
yeah,
What are we going to do first with it, though?
what is this?
We always use
Label.
it. Yeah, we're going to label. This little thing, let me look in your book, because some people in here are not very good at their penmanship. It's supposed to be like straight on this edge and then like a curve on here. It's not a V. Be real careful that you know it's not a V. It's important that we understand it's not a V, because sometimes we use this equation with the actual Latin letter V instead of C. So it would be this is what we sometimes use, and obviously we can confuse ourselves. This is the general formula for a wave. General. This one is specifically for light, which is why we're using it today. This isn't really part of your lesson, this is the part that's review. But you can see how you can fairly easily confuse yourself if you're using V for wave velocity and nu for frequency, which would be valid. You can, but they're very similar in shape, so let's don't. Anyway, C is, does anyone know? You probably read about this in your vocab.
Speed of light.
Speed of light in a vacuum. Speed of light in a vacuum. Remember to put two U's in vacuum, because it has two U's. What units for this, probably? Well, let me turn my picture in picture so that Camden can see it better. Can you tell me if that, like, does this shows up on the screen? Yeah, okay. Meters per second, yeah, someone said that. Was it Peyton or Lily? It came from the peanut gallery over here, but one of them said meters per second. That makes the rest of this really easy. Lambda is, you've already said, wavelength. What do we measure in the SI? What do we measure any length, whether it's wavelength or person length or room length in? We measure it in,
7 meters.
but the base unit,
Meters.
meters, usually meters. And then nu, let's have our little Greek alphabet up here. Nu is nu. Nu is
The frequency.
frequency, which is measured in. No, good guess. No. Well, what's left? We have meters per second. We
Just
know
plain
Oh, second.
seconds.
almost.
HZs.
HZs. That's not what I mean by hertz. This is a unit hertz, but 1 hertz is equal to 1 over seconds. Or a lot of times we'll write it this way: seconds to the negative first power.
Oh, our book says /s.
Yeah, per second. It also says, well, I think it says 1/s if you read more carefully. But this 1 divided by second, it's 1 over, it's what we call inverse seconds. So then obviously we all multiply meters times inverse seconds, we get meters per second of velocity. Questions about this? Let's do one as an example. Let's do it in a different color so that it looks good, I guess. I don't know. It already looks pretty good, I think. This is a nice looking notes. Thanks. Okay, let's say we have, and this will be a story problem, but let's say we have a wave with a frequency, oops, sorry, I used F when I should be using nu, a frequency of 1.6 times 10 to the 4th hertz, and we want to find its wavelength. Do we have enough information, first of all?
No.
It's going to seem like no, but we actually do, because what do we know about the speed of light in a vacuum?
It's
Oh, we
per
already know the speed
second.
of light.
We already know its unit, but unlike many things that we just know the unit, for a speed of light in a vacuum, we know its actual literal constant quantity, which is 3.0 times 10 to the 8th meters per second. So please write that down with your speed of light. So we always know this. That's why Lily was careful to specify speed of light in a vacuum, because the speed of light does change. But for this equation, we always use the constant speed of light in a vacuum, which does not change. 3.0 is actually, if you, depending on how many sig figs you want to use, I think the first 3 digits after the decimal are 0, so you can use 3.000. That gives you 4 sig figs. This is the face paint I made. What can I help you?
No, I got this.
It's just that this is a more exact measurement, so if we want to use more sig figs, we can use this one. But since our other given here only has 2 sig figs, we might as well just use 3.0 times 10 to the 8th. BT dub, how many will our find definitely have then? Sig figs.
Which one are we using?
We're going to use both of these.
Oh, 2.
2, so it'll definitely have 2. What should I do first here?
Write down
Write
your
down.
equation.
Write
Tell
down
me.
your equation.
C equals lambda times nu.
Lambda nu. It's very Greek up in
You
here.
know what?
Now what?
Lamba.
Go
Like
ahead. What do you think?
I don't know, lava just sounds cool, like Mamba.
Mamba. Good, I'm glad you brought that up. Very,
Well,
very
it
good
was a joke,
response.
but then I realized like none of you did, so then I just stopped.
Kylan has something else to remind us of. Say it again, Kylan.
I said it reminds me of a sorority.
Some of us, it reminds us of a fraternity or an honor society. Those of us who are intellectuals instead of drinkers, it reminds us of an honor society. I was a member of an honor society. I was not invited to fraternities. Anyhow, let's move on. What should I do next?
Manipulate.
Thank you, Lily.
I said it.
Everyone said it. Excellent. What should I do and why? Why not substitute now?
You should
Because
divide by nu.
Yeah, divide both sides by nu. So C over nu equals lambda. Now I finally, the satisfactory part is when I can substitute, which is, tell me what you write, Lily.
3.0 times 10 to the 8th over.
Oh,
No,
Hey, nice to be prayer.
Wait a
Meters per second. Thank you, Mitch.
Oh.
You say thank you to him, you say sorry to her. What should I write
How many
down?
times have we had?
Okay,
0, I bet. Lily, let's go.
okay, 1.6 times 10 to the 4th hertz.
Hertz. It's a little bit hard to see, well, first because I wrote it kind of, that's not what I'm talking about. It's a little bit hard to see how the units work out because hertz is 1 over seconds, right? But it's on the bottom. So if we have 1 over seconds in the denominator, what is that equivalent to?
It's equivalent to flipping it around and being seconds over 1.
Exactly. So seconds over 1 in the numerator, which is just seconds in the numerator. So what's going to happen here is
It's
that
going to cross out.
hertz drops out with seconds, and we're left with, I'm going to do it down here because it'll be even harder to see, meters. Math time. Who brought their calculator? Didn't Mr. Snitley,
I did. Wait.
doesn't Mr. Snitley buy calculators for everyone? Good. Thank you, Kyla.
Use this one.
Thank you, Kyla. What's that I see you
Okay.
looking at, bitch?
3.0
Let's have a talk about contraband while Kyla's doing some
Yeah,
math.
all the answers.
To
Just put it
the
away.
8th.
Thank you.
No, I was getting into them. I was getting like hell.
Good tea. You guys are
8
relaxing.
divided by 1.6 times 10.
Just no.
Bitch, you should be corroborating this.
I trust Kyla.
Did I do it wrong?
I
Should
you
I not
probably-
trust Kyla?
Let's-
Okay, I think you probably do need
Let me learn you
parentheses.
something about calculators here. Can you gather around the campfire quickly because we have some fun stuff to be playing. Yeah, you're part of the campfire, I guess. So we're gonna type in. Let me give you a little cheat code about calculators. If I want 3 times 10 to the 8th, I can just put 3, and then I use second comma, which is this little e. You see it?
Yeah.
So then that makes a little e, and that means the same thing as times 10 to the. So then I just type 8. So and this way I don't have to use any parentheses at all. So then I'm just going to divide by 1.6 e4.
I never knew that.
There we go. 1,800. Now I don't need that
No,
corroborated.
18,000.
Okay, I'm not always right. 18,750 meters. And these will start to be the fourth step. What is the fourth step? Do you remember? Check for.
So you
Oh,
plug in.
yes.
Good. I like that, and we did it. So let's do that. That's not really what I meant by the fourth step. But this should have 2. So what should be what instead?
What was it? 8.
It was
should be
18,750.
19,000. So nice.
So 19,000. Okay, great job, step 4. That's what I was talking about. I'm smart.
Everything in to make sure that it comes out equally.
Acceptable. Yeah, that's good. I do like that. That would be. I don't often say that's more work than I want you to do, Peyton, but you've done it. That's more work than I want you to do. What I would ask for you to do is just check to see if this is reasonable. And right now, this means almost nothing to you. Like, does it make sense for this wave to have a wavelength of 19,000 years? I don't know. But as you do more of them, you'll start to realize that there's an inverse relationship between the frequency and the wavelength. Obviously, as if we have our equation C equals lambda nu, C must stay the same. So if we have a great big lambda, we must have a tiny little baby nu, and vice versa, right? They're inversely proportional. They have to be. But you'll get a feel for whether this makes sense or not as you go on. Trust me. For now, if you want to be like Peyton, and we all do, then plug it back in and see if the numbers work out. I'm sure they will. And another way you can check is if your units work out. If your units work out, then your math is right. And they do. We checked that, so we're good. Okay. One more thing to talk about conceptually before I want to show you something in the laboratory. One more thing we want to talk about conceptually and a math. I know how you guys love math, so we'll do that. Which one do you want to do first, Mitch? No, Alexis, which one do you want to do first? I don't hear Mitch. Which one do you want to do first, the math or the concept, Alexis? Nice, good choice. Is everyone ready for this to be erased?
Yeah.
Camden, if you're listening, you can pause the video if you're not ready for it to be erased. At least it's taking a long time to erase it. Let's write down this next bit, which is we can use the frequency. I'm just going to write this down as a concept first, and then we'll do the math. We can use the frequency of light. We can use the frequency of light to determine its energy. We, who do I mean by we?
Scientists.
Scientists can use the frequency of light. Good people would make sure this looks like the letter nu and not a V. We can use the frequency of light to determine its energy. I'm interested, because I have told you this before, but you were freshmen, so maybe you don't remember. I mean, some of you were only freshmen last year, so you'll have an easier time remembering. But do you remember the relationship? We just said that wavelength and frequency were inversely proportional. What was the relationship between energy and frequency? Yeah, directly proportional. Good guess, Pam. You're closer than wrong. So, yeah, they're directly proportional. So conceptually, as energy increases, the frequency also increases, and vice versa. What we can do with that mathematically is we can show that the energy of a photon. What's a photon? This was one of your vocab words.
Is
Almost exactly wrong, Mitch. It's a particle without mass.
Mm-hmm.
It's a particle of. What's the root word? Yes. Photosynthesis has the same root word. The root word of that all being all of those. Photograph, photosynthesis,
Photo.
light. It's a particle of light. One interesting thing about light is that we know, or when we experiment with light, depending on the experiment, we can either mathematically describe light as a particle or as a wave, whichever is more convenient, because it has properties of both, and it always exhibits both properties all of the time. And it's kind of crazy, but do you remember when talking in the quantum mechanical model of the atom that at the level of the subatomic particles, energy and mass are really pretty much interchangeable? That like 3/4 of the mass of neutrons and protons comes from the strong force itself, not from the quarks that make it up. It's kind of the same thing with light. At that tiny little scale, particles and waves are interchangeable. Matter and energy is interchangeable. So both of these, the photon, which is a particle of light, and the quantum, which is the lowest amount of energy that can be transferred at all. That's what a quantum is. Quantum comes from the Latin word meaning to count, and it's just the tiniest amount of energy that can possibly exist. One quantum. We actually define it as the amount of energy it would take to raise one electron from one orbital to the next, and that's what we're going to talk about in the lab. But both of these are calculated by this equation, which I want to make sure I put in the right order. It doesn't really matter which order it's in, but it's this fancy h times nu. Let's describe it up. The E in both cases is energy. What do we measure energy in science always? Joules. Well, I have a lot of videos about joules. If you want to learn about joules, hey Peyton, if you want to learn about joules, Joule, then you can watch the other videos. The fancy H is Planck's constant. This is named after a German physicist called Max Planck. And the frequency is frequency. That's stupid. The nu is frequency measured in, again, hertz. So if we have hertz, which is inverse seconds, and we know our product is going to be joules, what must the unit for Planck's constant be?
Joules per second.
Yeah, joule seconds. Joules times seconds. Joule seconds. Sometimes if I'm being specific, I'll say joules times second, but we usually just pronounce it joule seconds. Planck's constant has a known value, and Planck's constant's value, just like the speed of light, they're not the same value, I didn't mean that, but just like the speed of light, they're both known. We know an exact value for Planck's constant, and for Planck's constant, H is always, fancy H, is always 6.626 times 10 to the negative 34th joule seconds. We won't have time to do an example one of these. These are all over your chapter review, though, and I'll give you a worksheet. So you will have time for examples, but we won't do that on this video today because I want to move on to the next conceptual thing and to the exciting thing in the lab. We've only got 12 minutes. But this is not a complicated problem, is it? It's a 3-variable equation, just like we had been doing. One of them is a known quantity. This is always 6.626 times 10 to the negative 34th joule seconds. This will be given, or this will be given, and you manipulate to find the answer. Questions about this before we move on? Alexis? Mitch? Peyton, you're good?
Yeah.
I can see you're still writing, Kyle, so I'll wait.
Does that
But
say
I'm also very impatient.
joules times second?
Yeah, joule times second. And this you need to have memorized, by the way. Same with the speed of light. You have to have both of those quantities memorized as well as the units. Good, Alexis? Okay. Shoop. That's the sound of a person erasing. Last thing before we can progress into the laboratory. Camden, you can't join us in the lab, but maybe someday you will be able to. Let's talk about the electromagnetic spectrum. Real quick, this is review also. Oh golly, I've really gotten carried away. Whatever. I started doing it like that. Whatever. And then also the M is supposed to be up here. Thanks, Peyton. Your laughter in mockery really makes me feel like I'm doing a good job. Magnetic spectrum. That looks better. It's hyphenated, so it's not things that are always hyphenated. How should we set up our electromagnetic spectrum? You've seen this before. If we have increasing frequency as we go from right to left on our chart, and increasing wavelength as we go from, I said it backwards, right to left, this one was left to right. Increasing wavelength. What should be on the leftmost side? I expect you to have these memorized from last year, Lily. Say it. You were about to say it. I can tell from the shape of your mouth that you're going to say it. Radio waves. Radio waves. Next.
Microwave.
Is Lily going to do all of them? The micro
I don't remember.
waves. Microwave oven. What's true of the microwave oven that relates to this? Yeah, it does cook stuff. Why? The microwave has a certain. The frequency of this is modulated to be exactly that of the resonant frequency of water, and so by emitting there's a little thingy. I didn't mean that. There's a solenoid inside the microwave that emits. There's a solenoid inside the microwave oven that emits microwaves of a certain frequency, and those cause the water molecules to vibrate faster and faster and faster. And as molecules vibrate faster, what do? That makes the whole thing heat up. So if there's water in your microwave, that heats up. If there's not water in your microwave, nothing happens. An example of this, Skylar was doing a lab with a balloon in the microwave a couple weeks ago. She was trying to make the balloon warmer in the microwave. I didn't know if it was going to work or not. I thought it probably wouldn't, but I felt bad for it. Anyway, she put it in there, nothing happened. She put it in for a minute, and it did not get any hotter at all because there was no water molecules to vibrate. The microwave oven is tuned to a specific frequency to just do water molecules. Anyway, what comes next?
That's why when I always forget to put the water in my oatmeal, it burns it.
It burns it because there still is some water molecules in the oats, and there's just a few of them, so they vibrate super fast, and then they're like, well, I'm on fire. Next one, microwaves. After microwaves? Infrared. Infra, Latin prefix for... You guys should know your Latin. We did this in the MTSS days last year. Infra, Latin for?
Heat?
No, below red, meaning it has a lower frequency than red visible light. The next very narrow band is what we call
UV.
visible lights. Not light. We normally just call it visible light. That's supposed to be yellow, but because I was trying to draw Peyton's hair on top of that blue wave earlier, it looks nasty. Why do we call this one visible light, homies?
Because we can see it.
Because you can see it. This is the light that is visible to you. What is making these colors of marker show up as different colors on your eyes. The what?
They're
The
reflecting.
yes, that's all right. But what part of the wave is making different colors show up?
Frequency.
The frequency. The frequency. It's very important that you know that because that's what we're going to talk about in the lab if there's time. Next, after visible light,
X-rays.
no,
Just kidding. It's ultraviolet.
you're right. It's ultraviolet. I've switched fonts.
Then it's X-ray.
Leave me alone. And then it's X-rays. X-rays, and we've already learned about gamma a little bit, haven't we? What was gamma? How was gamma related to what we've already done?
You're doing radiation.
Yeah, gamma is also emitted in nuclear radiation. So which has the highest frequency? Gamma rays. Which therefore also has the highest energy?
Gamma.
Yeah, and pretty much anything from about halfway through ultraviolet on has enough, what we call ionizing radiation. It has enough energy that it can knock chunks off of your DNA, which can kill cells,
Why we
usually.
use
99% of the time kill
UV
cells.
light,
Yeah, go ahead.
which is why we use UV light to like take the germs off of our products.
Yeah, exactly, because the thing that makes the germ be alive is its DNA. And so we have the UV light in the goggles, and that's why you're supposed to keep it shut while you're doing that, because it will also harm your cells. Where else do we see harming of cells that's intentional, besides in the germicidal?
We talked about it. Chemo.
Cancer trying to stuff.
Yeah, chemotherapy treatments, because it kills all cells. Usually it's targeted to kill the cancer cells instead of the regular. And also in tanning coffins. You ever heard of tanning coffins? It's like a tanning bed. That's what my biology teacher in high school called tanning beds, because you're deliberately giving yourself cell damage to ideally be brown, but usually starts out red. And that's why you get a sunburn, by being in ultraviolet light in the sunlight. And then X-rays, you have to wear the little lead apron so that you specifically over your reproductive organs so that those cells don't get damaged, because that, remember, we talked about this last year, but since they're reproductive cells, it's just one egg and one sperm coming together to make a person. And so if that one egg or one sperm happens to be damaged in an X-ray booth when you're 6 years old, and then those come together to make a person, the person that is made doesn't have the right DNA. And that can be troubling. So we always want to be careful to protect ourselves from X-rays. And then gamma rays, almost no use other than harming things. It's emitted in outer space. It's emitted by nuclear radiation, but we don't normally interact with this. We do have a little bit of time. Let's go in the laboratory. Are there any questions that might benefit Camden, since she's going to be watching this, or you, about the concepts of this chapter? You need to know the electromagnetic spectrum in order. You need to know how to use the equations for the speed of light equals wavelength times wavelength times frequency, and you need to know the energy of the photon, the quantum. And then you also need to know how it relates to the quantum mechanical model of the atom. Questions?